It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Today we're going to be talking about the Doppler effect and how sound can be perceived differently by changing the speed. We're also going to be talking about redshift, blue shift, sonic booms, and all that fun. So to start off with, here's an opportunity for any students who are planning on going to college and would like a scholarship. The AAPT, that's the American Association of Physics Teachers, high school physics photo contest. Many years you can take a picture of either something natural or something contrived, and you take a picture of those. If you do so and you are the winner, you get scholarship money. So if you have any further questions, you can ask either your physics teacher, and they can tell you all about it, and yeah, we can get you some scholarship money. All right, so Doppler effect. So to start off with, the Doppler effect is kind of an idea that if you want to imagine yourself as a bug bobbing up and down in the middle of a quiet puddle. Now, suppose that bug is not going anywhere, but merely treading in a fixed point. Well, the crest of the waves are going to be concentric circles. And because of those waves, the wave speed is the same in all the directions. The bug's frequency, anywhere at any given moment, the distance between the wave crests will be the same. So that means the wavelengths will be the same and nothing really, it's just constant little circles. So waves encountered at point A compared to point B, opposite sides of them. So if it's on the left side, if you're over here, and compared to somebody else who's over here, point A will receive just the same amount of frequency as point B. Now, suppose that little bug instead is moving laterally across the wave, moving, jumping, and then moving, jumping, and moving towards, let's say, point A over here on the left side of the screen. Well, then, and he's traveling, and this is the key part, traveling less than the wave speed itself, so less than what the speed of the wave in the water. Well, these concentric circles are no longer concentric. The centers of the circles now are moving in the direction of that swimming bug. And even though the bug is maintaining the same up and down frequency, so it's going up, down, up, down, up, down, compared to when it was just doing it in the middle, the frequency observed by B would encounter more often than A. So we're going to show you here a video of this, and it will make a lot more sense. The observer would counter higher frequency. This is because each successive crest has a little bit shorter distance to travel as they arrive to point B, more frequently than if they were traveling at point B. Now, this change in frequency is due to the motion of the source, or the this change in frequency due to the motion of the source or receiver of the sound wave is called the Doppler effect. So here's a picture of it. So as this car is coming towards, they're producing a sound. Now, it's not changing the sound. The sound is not changing. But as it's coming closer, each successive circle, that first circle is over here, the center circle was over here, and now it's over here. So the truck is moving closer and closer. So the people over here on the right side of the screen are going to hear at a higher pitch than the people on the left side. The greater the speed, the greater the Doppler effect. This is the reason why we hear fire trucks and know if they're coming at us. If you ask, what does a race car sound like? You go, meow. Well, what are you doing with your voice? Well, you're increasing it, weep, and then when it goes away from you, meow, it goes away. So as it's approaching, the frequency actually gets higher, and as it's retreating away, it gets lower. So you can hear a fire truck of whether or not it's retreating away from you or if it's coming at you based on the fact of that sound of whether it's going louder or softer, or higher pitched or lower in pitch. You also have a softer and louder, but mainly you hear it based off of the fact that the sound is getting higher in pitched. Now, in physics on the job, police cars use that same principle, except for they shoot out radio waves, hits the car, reflects off. Now, If it comes in and comes back and it's exactly the same frequency, we know that it had a perfect reflection, and that means the car is not moving. But if it comes, hits in, and then as the car moving towards the cop car, those radar waves are going to be built up a little bit closer, and they're going to be a higher frequency. Compared to the receiver, you can do some little bit of math, or in the computer does a little bit of math, and it determines the speed of your car. Bats do this. Bats will throw out their voice. They make a sound. It bounces off a bug, and they know exactly where that bug is. And if the bug is retreating, it will have a lower frequency. If it's coming at them, it will have a little bit higher frequency. So not only does the bug know where the object is, but it also can tell if it's moving or not. So some people actually can do this when they were blind, and we'll watch that video.
Ben Underwood is blind. Both eyes were removed when he was 3, leaving him with no vision at all. So how on earth does Ben do this? And this? And even this?
I don't think I've ever come across somebody like Ben. You know, he was quite unique.
Ben lost his eyes to cancer, but unbelievably, he's taught himself to see with sound.
If he chooses to go out there and ride that bicycle, let him ride the bicycle.
It's got to be very smart. Somewhere in there, it's a little genius going on.
I don't consider myself blind. Ain't nothing wrong with me.
Ben has no guide dog and never uses a white cane. He's not even using his hands. Instead, he sees with sound. He makes a sharp click which bounces back off nearby objects. Amazingly, Ben's ears pick up the echoes and he can precisely locate where things are. Ben is the only person in the world who sees using nothing but echolocation.
Well, I've been able to tell where walls are and where things on the ground are. If I click down, then I can hear them easier. But if I'm walking, I'm just clicking over it, it's not gonna get it. And I can tell where desks are in the classroom and stuff like that. I can hear the wall over there, the couch over there. I can hear the wall behind me. I can hear the wall over there and the TV and the computer. Yep.
Ben, I need a towel for drying because I don't have all my kitchen towels in here.
All right, Mom, I'm gonna go get it.
Ben's echolocation is so good that at home his mum, Aquanetta, Uncle Kerry, and brother Isaiah make no allowances for his blindness at all.
When I was a little kid, I didn't really know he was blind. I just knew he was my brother.
Did he make it? He's determined to do what he's gonna do. And he refuses for somebody to label him as blind. You see this kid that has a whole different way of thinking. It's magic and it's real.
I don't think I've ever seen anyone quite as remarkable as Ben, nor have I seen anyone quite as remarkable as Ben's mom. And I think that's a lot of the secret to Ben's amazing talents.
He knows that there's nothing impossible for him, you know, and it's not.
Now, when the speed of that medium is great as the speed of the waves start building up on the front side. So they become so built up, there's a it kind of builds up, and if you break through that wave barrier, you can break it, and this is what we refer to as a sonic boom when the waves build up. So we're going to watch a video about that. All right, so when can barriers, sound barriers specifically, be broken? Well, when a bullwhip hits and does that, the tip actually is moving faster than the speed of sound. You also have the first vehicle to ever break was in 1948, and it was a rocker-powered vehicle. and then that was in California. Chuck Yeager was the first person to break the sound barrier in a vehicle, and that was in 1947 when he flew the Bell X-1 at Mach 1, Mach being the speed of sound. So Mach 1 is the speed of sound, Mach 2 being the twice the speed of sound. So here's a car. This is the Thrust SSC team car. And this car, you can see the ripples. Those are the ripples that we're talking about. You kind of see them distorting in there. And as they reach, they'll actually break through those ripples when it builds up in the front of the car. So when something travels faster than the speed of sound, it is said to be supersonic. So you can see here, there's a bullet traveling at 2.45, Mach 2.45, so twice the speed of sound. And you can see as it's breaking through that wavefront right here, and it's going to break here through this wavefront, and those wavefronts is what you're going to get that audible sonic boom, that crack of a sound. When that conical shell compresses the air in front and sweeps it behind, they reaches the listener on the ground. It is said to be the sonic boom, or that big large boom.
Sound travels at about 760 miles per hour, or 340 meters per second. That's about 661 knots on an average day at sea level. And sometimes you can almost see it. Going close to that speed through air can cause some unusual visual effects. What you're looking at here is a NASA image of an SR-71 bending light waves from the pressure differentials it's producing. Air's pressure and temperature both drop when airspeed increases. Rapid changes in density can be enough to bend light like a lens. How does it happen? Airspeed increases as it flows over the form of an aircraft pushing its way near Mach 1, the speed of sound. That means that even aircraft slower than the speed of sound can accelerate the air moving over them beyond the speed of sound. As pressure all around the aircraft drops, that air cools. And as air cools, its ability to hold moisture drops. So if there's enough moisture, you'll see it form in clouds that appear attached to the aircraft itself. But the cone-shaped clouds you see aren't in fact traveling with the aircraft. Each section of air is spontaneously reacting to the temperature and pressure change induced by the aircraft's body sliding past. Then there are the shock waves. Shock waves are formed by the air that can't get out of the way fast enough, forming a pressure wave. We perceive that pressure wave as sound. Aircraft actually usually produce two booms. They just reach us so quickly in succession that we can't distinguish the two. All of these factors are quite normal and have come to be expected in images that capture supersonic, transonic, or even near supersonic flight. But on rare occasions, we do get a glimpse of something special. At Kennedy Space Center on February 11, 2010, an Atlas rocket launched into ideal conditions for showing off shockwave. And this is the result. We hope you've enjoyed this little tour of visual and auditory speed of sound phenomena. Visit avweb.com for aviation news and inside information for pilots. This has been Glenn Pugh for avweb.com. Thanks for watching.
Now the Doppler effect also has an apparent change in frequency from the light. So not only does it do sound, but it also applies to light because it's all waves. Doppler effect applies to all waves, not just sound. So in light, if something comes at you, the light is going to be higher in frequency. And we call this blue shifting. When an object is approaching you, the object appears higher in frequency. Now I will tell you it's not going to be bluer, but the color of it is going to be ever so slightly shifted to a higher frequency. So reds are going to become a little bit more orange, orange becomes a little yellow, yellows become a little bit more green, blues become a little bit more purple. Okay, so everything kind of just shifts. Now, you could not see it with your naked eye. You would have to be going close to the speed of light in order for any object to appear a different color than what it actually is emitting. This can be done with using telescopes, and very sensitive machines can actually detect it. On the other hand, if it's object going away from you, it's going to shift towards the red side. So your purples are going to look more blue, your blues are going to look more green, green's going to look more yellow, yellows are going to look more orange, and oranges are going to look more reds. Again, not everything's going to look red, it's just going to shift ever so a little bit longer wavelengths. So here's an example of that shift. As this object is moving towards this side, you have that blue shifting. As the object is receding away, you have that red shifting. These are longer wavelengths. Even though each little circle is exactly the same size as its predecessor, it is going out in the same frequency. Beep, 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 beep. It looks like it's hitting this person a lot faster. It's hitting it at beep, 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 compared to this one where it's hitting beep, 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 beep. So it appears higher. So this could either apply for sound or light. So here's when we in astronomy we use this exact same thing. This is a reference from a laboratory source, and you can look here. This is from a star, and we can see how ever so slightly these lines shifted ever so slightly to the blue side. Thus, this spectrum, these rainbows, show us that whatever this object, this star, is moving away. Now here's the opposite. Here's a red shifted one, and it's ever so slightly to the left of the lines. So the star is moving. This one's moving away, while the blue shift is going towards us. Weather, we use the same thing for weather. We send out a radio wave, hits off a cloud, and reflects back. If the antenna sends out a radio wave and the object comes back, and the clouds are coming at us, they're going to be a little bit higher frequency than the original radio waves are sent out, and thus we know that the clouds are coming at us. And if the clouds are moving away, it's going to be a lower frequency than what was sent out, and thus we know that the clouds are receding, and thus we can tell that the clouds are receding away from us. So what would it mean to astronomers if all but one galaxy is redshifted? All the galaxies we can actually see in the universe are redshifted except for one, which is the Andromeda galaxy. It's blue shifted. Well, that would mean that all the galaxies are moving away from us in a longer wavelengths and lower frequencies, and then the light is emitted by the galaxy itself. So the galaxies are receding away. This was a big thing. Edward Hubble, with the Hubble Space Telescope, was named after. He determined this, and he realized that all the galaxies were moving away, and that if you rewind time, it created what we call now the Big Bang, that all matter was started at one point and then spreading out universally throughout the universe. And this was the big thing that showed us that the universe is expanding. So if a local astronomy club wants to create a t-shirt which demonstrates the Doppler effect, what colors should they have on the front and back? Well, the front, if you're running it towards you, you should be seeing the blue. And if it's on the back, it should be red. So, if you have any further questions, please go ahead and ask your teacher.
The Doppler effect. In Sheldon's words,
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it.